Okay, so we have prepared also a list of questions. Maybe we can start with this, a few questions just to break the ice. So the question we came up with first is the Turing test for robotics. What should be tested in an autonomous system to guarantee its functionality in unstructured environments? So repeat the question, what should be tested in an autonomous system to guarantee its functionality in unstructured environments? So who would like to? it's a tough question.
Yes. It's a tough icebreaker.
I can start breaking the ice. So, for example, in our lab, we are focusing on agile navigation of quadrolators, and we also talk to a lot of companies. And depending on the task, there are different ways actually to test the performance of the system. So we identify three axes: accuracy, efficiency, and robustness. So, for example, in inspection, cinematography, it's very important to be able to follow a given trajectory as accurately as possible, but also you want to be as repeatable as possible. So being able to also identify obstacles. So you want to have a very high success rate. In other tasks, instead, it's very important to be efficient. So, for example, to be time optimal. So you want to pass through a sequence of waypoints. For example, think of inspection of power lines. So you need to pass through power lines, power mass as fast as possible. So these are things, for example, that, in my opinion, should be tested in autonomous drone system to guarantee its functionality in these environments. But I would like to hear also your opinions. Yes.
Yeah. So I think the proof is really in the pudding. I was talking to somebody from KUKA a couple of weeks ago, and they had introduced some fancy cobots in the factory floor. They came back a couple of months later, and they were all on the side, and they were still back to the old ways of doing it. So I think that's the real test. Introduce a robot in the wild, so to say, come back a month or two later. If there's still news, you managed.
Also, as you said, talk to the companies, understand their needs, go visit them to understand exactly what is that the environment that they want to operate. David?
Yeah, sure. I think the testing depends very much on what we know about the target domain. And I don't think that there is a universal answer to this question. What we know about it, it's about the, so there are certain things that are unknown, but they are known unknowns. If we know the unknowns, we can try to test for those things. If we don't know anything about it, it's very difficult to test for anything, right? So if we don't know anything about, at least we have to know the domain itself. It doesn't matter if it's a locale or it's a particular task or things like that. If we have access to that target domain, we can try to test over there directly. So the real world is its own testing environment, right? Now, I can also relate an interesting experience I had earlier regarding this issue. Right, so you have so there is this TCAS system, which is the aircraft collision avoidance system that's flying out aircraft these days. And because of the increasing density of air traffic these days, that's the FAA is developing new systems, and they contract with Lincoln Lab and stuff like that. Eventually, they have to do something, and in some part of the core collision resolution logic, Lincoln Lab discovered that a Palm DP solver tends to be useful, and they contacted us. And eventually, whatever, cut short some details about this. So essentially, when I heard about this, oh, this is wonderful, right? So I have this Palm DP solver, and I can solve for the optimal, and I can kind of prove, I can guarantee you with high probability, blah, 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 blah. And this is the like performance, theoretical performance guarantee I can give to you, right? So this is one. If you think about, I mean, verification and testing in general, if I can provide you a theoretical guarantee, all of us should feel very happy that, especially for a safety critical system like this. Well, when we tell about Lincoln Lab and their responses, and never mind about your theoretical guarantee. Right? So this is what you need to do, right? So we have a simulator over here. I mean, in the Lincoln Lab, the FAA provided a simulator. And this are I forgot the details, 6,000 scenarios which are gathered from the real US airspace traffic, the traffic data over there. You cannot have access to the simulator. You can do whatever, do your policy computation and stuff like that. Once you finish your compute, you can give us this policy and we'll evaluate our this simulator and on this real world data. And this is what it means to test. If you can pass this test, even in relative terms, for example, compared to whatever TCAS is doing right now, then you kind of can claim that this has been improved.
Ingmar, would you like to
Sure.
say anything? Yes.
Yeah. So I don't think you actually mean the Turing test, right? You're actually talking about regression testing, or you're in some way like integration testing, you're unit testing, you're doing any of those things. And of course, I mean, that we can do lots of. And as David says so eloquently, that very much depends on what your application is, right? So every application ideally comes with a playbook. And when you develop new components, you fairly routinely, hopefully, develop through that playbook and test against that playbook. In fact, in machine learning, we do nothing else, right? We have a test set, and that is our playbook when we say this is how we need to perform. It doesn't come with any guarantees, of course, and I have to admit that I'm skeptical about verification and its sort of practical uses in environments that aren't predictable, which is basically all of them, right? But I'm very happy. I'm very happy to be schooled on that one.
Animesh?
After all of the people, I don't even have much more to sort of practically add. I think the practical version of the solution would be, as Ingmar said, a component level testing where you say, okay, test perception, test low level control, test motion generation in presence of procedural obstacles, and then do some sort of integration testing. But I believe the spirit of your question was, how do I do testing for cognitive failures? I wish I knew the answer.
No, we didn't get so no, not on concrete things yet. No. Okay. So I would like to hear also from the audience. Is there anyone who would like to comment? Yes, please come here. Yeah.
Hi, I have a question for Animesh. So it sounds like from your talk to you, like sometimes domain randomization is important and sometimes it isn't, and we should figure out when to do that. And we have a simulation with some parameters that we try to identify. Can we identify the uncertainty of those parameters as well and use that to inform the domain randomization? And can we, what sort of simulation parameters can we do this for? Like I can imagine it being relatively easy for something like a dynamics model, but maybe more difficult for how to compose the scene. Do that. How to inform the randomization from data.
If I understand the question correctly, you're talking about what sort of parameters should we pick for active domain randomization? Can we build uncertainty models on parameter estimates? The answer to both of those questions would be yes. We can indeed do active domain randomization and uncertainty estimation. I think the main takeaway from the works that we were trying to do was, when we do domain randomization, we are essentially trying to build a robust controller, and robustness does not come free. So, like, there is no free lunch in that sense. So if you're randomizing everything very harshly, then we might end up with suboptimal control, which may not be necessary for transfer. And then coming back to the practical thing, if you know something about the domain or have access to the domain, then at the risk of sounding old school, performing old school system ID is actually a pretty good idea. And system ID can be done in a variety of ways, including Bayesian methods, which can do parametric uncertainty, and with new methods where you can either train policies which are conditioned on the parameter estimates. So there are ways people have done that, or you can now use the parametric uncertainty to adapt the policy in the simulation live, because we have reasonably fast simulators. Both of those have independent lines of work. Neither of them I would claim to be mine. One of them has been led by Fabio Ramos, Bayes Sim, and this other line of work has been used for parametric condition policies. I think has been very practically used in a lot of legged locomotion work from Berkeley, from CMU, MIT, number of people. So yeah.
That's one quick question. Like how broadly can we do system identification? Like, can we do it for environments that like you said, a kitchen, like a kitchen is composed of a number of things. Can we identify a model for kitchens or the range of possible kitchens? Or like if you had a database of some type of room, can we parameterize that somehow and then generate instances of an arbitrary type?
That would depend on the problem you're trying to solve, right? So you could argue that I'm trying to do state estimation of let's say kitchen objects. In that case, you would basically be building a large scale sort of visual estimation system, which would need a different kind of randomization, and the evaluation testing would be different compared to, let's say, if you were doing randomization for physics parameters of, let's say, your refrigerator. Is it spring loaded? What is the weight and the mass of it? The inertia of that object. So I think this would be very target dependent. In general, what we did for the mobile manipulation work, we did the control in end effector space, operational space of the end effector, and we did not randomize the masses of the objects per se. We assumed low-level access, but we did randomize poses of the objects and relative poses with which you would, let's say, initialize the robot. So a lot of it was kinematic randomization rather than dynamic randomization, if that makes sense.
Thank you.
Sure, thanks.
There are other questions from the audience.
Please.
Okay, so I have a question for each of you. What is your favorite simulation platform or physics engine? Now, give bonus points if you name a software package that isn't your own.
A software package that is?
Not your own.
That is yours. Okay. Who would like to answer first?
I don't necessarily have a favorite one. My team has been using Pineau a lot, and so far I've been pretty happy. Pineau?
First, I'll state that like a simulator is a model, all models are wrong. I'll pick the one that is most useful to me. So having said that, Python is good, but it's not differentiable. I want a differentiable one, and the one we are using right now is a diff-type-G. It's a general purpose particle-based simulator. They have a wide variety of different kind of objects, both rigid and deformable. It's nice.
Ingmar?
Tricky question. So I have to say, my gut feeling is I don't care. But actually, that's not entirely true, because it depends on what it is you're trying to do, right? So if you're looking at RL, there's a certain choice that you make, and I can probably say that. So something like Isaac would be great. If you're looking at something where you need sort of more accurate physics, you might make a different choice, but I think ultimately it depends on what it is you're trying to do. That said, I think it also matters who has implemented what benchmark in what framework, right? That is a pretty strong pull. Let's be clear about that. So it's not just about how good the physics engine is. It's also what kind of support you get in terms of the community and in terms of the benchmarks that you want to be running on. So,
Animesh?
I think the last point that Ingmar made actually is more important. One could argue that the correctness and the fidelity of the simulator is actually not the primary decision-making, let's say, variable. Usually it's like ease of use. Like how easy can we get on board, what frameworks, what environments, what interfaces exist to, let's say, ROS, motion planners, and so on and so forth. And then the other aspect is actually increasingly so, many of these simulators do not come with very good renders, right? Like the default render with PyBullet is pretty bad. diff-type-G is a custom renderer. So if you want to do anything where you want visual, let's say, accuracy, or if you're building any sort of perception pipeline, then it's not just simulation, but actually rendering system. And that, to still answer your question, I think if I were to say, if we were allowed to say, I would still say I6 which is sort of all of it. But if I was to say others, which are not ours, I think of late, I saw simulations from Algorithmic to be very interesting, although they're not free to use. They can simulate fairly interesting, let's say, phenomenon that are generally considered hard to simulate.
Awesome. If I can just ask a follow-up. So you're kind of touching upon this with your points already, but I wonder, how do we balance heritage for community adoption and leveraging technological advancements? I think there's heritage versus adoption, and maybe we could have a discussion about community consensus or coordination for these simulations.
Is this pointed at me or?
No, not
I
to
hope
anyone.
some-
Would like to...
Yeah, please.
Like Animesh was just saying, one of the most important questions is always going to be what's already available. And that also comes back to what we were discussing, I think, in the morning a bit about benchmarking. So if somebody's putting out a benchmark that's interesting and is getting picked up, then there's going to form some consensus around it, like you see the Mojoko for the OpenAI Gym benchmarks, for instance.
I think I would have to go with, I don't really understand the question. But what's the tension between heritage and community adoption? And I'm sort of with Animesh here. I think old school is perfectly fine, just saying. But what's the tension? I don't really understand that.
So it's a spectrum between heritage and advancement. So if there's new stuff coming out, then you need to transition.
I think legacy.
Yeah.
Right. But is that actually a challenge? Because I find that, so generally the steer that I give my students and the thing that we work with is if there is a benchmark or a publicly available data set or something that we can somehow connect to other works out there that actually meets our requirements, then absolutely we would use it. And if there isn't, we have to have a really good reason for why there isn't. And then we can create a new one, right? And hopefully that is done in such a way that other people can use that as well. And I think that is true for simulators as well as for benchmarks, actually as well as for code releases, right? I think that's why it's important. So in a way, I almost feel like there's a marketplace that works, right? So I don't really see that legacy or heritage versus adoption challenge. But if you perceive a concrete challenge with that, a concrete issue, I would love to hear about it because I'm not seeing it. So maybe I'm missing something.
I think if I understand or if I interpret the question correctly, usually adoption is guided by one, like benchmarks that people are using and you are required to report on similar benchmarks, and two, ease of use. A good example could be, let's say, OpenAI Gym using Mojoko, right? Independent of like commenting on good or bad of it, the fact that it became very popular, especially in a time when it was not even free, actually, despite the fact that there were several free alternatives, was mainly because one, for students in machine learning and robotics, it was very easy to use. Like getting on board was very easy. And two, other people were reporting on it. I think I do want to point out one thing in simulators to perhaps answer your question, how can the community coordinate? When we as roboticists talk about simulation, we are actually merging 3 or 4 things. It's one, the physics solver, a renderer, asset library, and the interface. Mostly as roboticists, we are not tinkering with physics solver and the renderer. We are mostly just writing interfaces more often than not, and assets are often just given to us, or we just sort of scrape the web for it. What would be a good idea for us to do is to build interoperable platforms, very much like ROS, where I can swap bullet with Mojoko with a different solver that you can write a custom solver, diff tai chi, while keeping everything else the same. I know this is an aspirational goal, but creating something like that would enable people to not, let's say, as you said, stick to legacy because interoperability exists, and comparison would be easy as well.
I should totally address what the example that I was thinking of. There's a lot of adoption for ROS1, but there's a push to write software packages for ROS2 moving forward. So, you know, there's not this backwards compatibility for some code packages that are commonly used. To answer Ingmar's
I barely heard that. I'm really sorry. If somebody could tell me.
Maybe, yes, do you want to repeat the question here? And then we go on.
I'm sorry, yeah. This is the last everybody here. Okay, so Animesh answered my question and potentially your confusion, Ingmar. So what I'm experiencing is that there is a ton of adoption for ROS1, but there is a push to adopt ROS2. But there isn't this backwards compatibility for some software packages in ROS2 that are used in ROS1. So that was kind of the example that I could think of.
Right. But to me, it comes back to utility, right? Which is exactly the same argument. So in a way, that's what Animesh said as well, because everything that he just mentioned, I can summarize under this notion of utility, right? And so I think if there is enough utility to enough people, the community will provide this and it will get supported, right? And I think I don't know whether that answers your question, but I still think that is true. To Animesh's point of interoperability, I think that's a really beautiful view. That would be a nice world to live in. But the problem that we have or have had is not one of sort of too little entropy in sort of the simulators that we use and the physics engines that we use, right? The problem that we have is not that we can't plug too few things together. The problem is often that, you know, we're very quick at creating things that suit our problem and not care enough about other things that also suit our problem that might be a more appropriate benchmark, right? So for me, it's almost like the opposite.
Okay, I would like to move on. So if we now compare the progress in robotics to computer vision, as Angela showed this morning, so in computer vision, there have been a lot of benchmark data sets, for example, Kitty, ImageNet. So we haven't had so many in robotics. So many of you today spoke about manipulation. Maybe it would be interesting to discuss about how is the progress in manipulation going. So are you guys using the same benchmark simulators? But careful, what I mean by benchmark simulator is not the same simulator. It's but a benchmark, where basically there are tasks that provide the same initial conditions and therefore allow you to basically measure your progress against the baselines. So that you take a table from paper, copy paste the results of that paper into your paper, and then you just add your results. That's exactly what people do in computer vision, CVPR. No, this is exactly how the progress goes. I would like to understand, is this also happening, for example, in the manipulation community?
So, okay, let me start with something slightly different. In computer vision, yes, there are lots of benchmarks, but there also seems to be somewhat a trend of overfitting to the benchmarks and fighting about whatever third digit after the comma. So there's also some danger in that. But to answer your question, there have been multiple benchmarks and multiple tasks that have been proposed on peg insertion and assembling something with gears. But so far, and I have no clue why, none of them really have picked up, in a sense that that's the one standard that everybody is doing and needs to compare to. And quite often what you see is that you see similar tasks, but with some slight variations, which then makes it impossible to really do what you were just saying, to copy paste the lines and have a fair comparison through that.
Okay, so do you think it would be useful to have benchmark tasks in a specific simulation environment where the same initial conditions are provided, the same things, so you can basically just run your algorithm and then report the results into a paper? And that's how you compare against the others.
Would be nice to have, yes.
So, okay, why do you think, if there are, because people have shared these benchmarks, why do you think that they weren't picked up?
I don't know, because it's easier to sell your paper if you can say that you did something truly new. What do you think?
All right, I don't have an answer, but I can think about over here. David mentioned about manipulation in particular, right? But let's do a comparison with navigation and autonomous driving, right? It seems to be that it's more likely, just intuitively, it's more likely we have autonomous driving navigation benchmarks or simulation environments than compared with manipulation benchmarks and simulation requirements. Right? I think that has to do with the nature of the task domain itself, in particular its variability and the standard input format. Right? So this is particularly obvious if we compare with computer vision. Computer vision is very challenging, of course. But there's one thing that's simpler in computer vision compared with robotics, which is that they have a common input format, which is this array of pixels. No one disputes on that. Right, suppose we try to do the same thing, let's say we create a manipulation benchmark, even in simulation. Right, so what does that really mean? Do we agree on what is the n factor? Can we agree on that? Probably not, right? How many fingers? Top grasp, side grasp, like affordance and all these things. None of them we necessarily agree on. I think that at this level, I think that manipulation in particular has this greater variability in the task domain. If we say benchmark, well, the purpose of benchmark, or at least a good benchmark, is to have certain predictive abilities of the general performance. And that predictability is necessarily compromised by the variability of the task domain itself. Okay. I think it is for this reason it's harder in the manipulation domain to create benchmarks, because we can indeed, if we just sort of come down hard and standardize on some format, we probably would have that particular task. But yet, once we succeed in that, we may not, the implication of succeeding on that benchmark may not say a whole lot about the general domain itself. I think that is a real difficulty.
I agree. However, I also have a counter argument. There are standard manipulators that come with some sort of standard grips that many people are using. Wouldn't be already sufficient to integrate them in a benchmark simulator and then start using them in order to advance the progress in specific with specific manipulators and grippers? So if you define basically the gripper domain and so on.
Yeah, I definitely think so. I think one is that if we have already identified certain promising manipulator arms, hands with sufficient capability, we also have to add in a suitable object data set. Right? I think that there are efforts along that lines. And once we put them together, and we would have a general purpose manipulator and a manipulation domain, where the success on that benchmark will tell us, inform us on the progress of the field.
Ingmar.
That's a good question. I mean, that benchmarking question comes up often and in many places. I'm sort of divided on that, right? Because on one hand, I agree that overfitting the benchmark is not so great. On the other hand, I think we do have benchmarks, right? And I don't think a benchmark is one that everyone has to adopt. It's a question of, do we have them and do enough people find it useful for us to progress science in a particular domain, right? And I think that does exist. I think the part of benchmarking that often gets forgotten is that it's not just about the problem set, but it's also about the models, right? So open sourcing your code for other people to try on their problem domain is almost as important as having a particular benchmark that everybody uses, right? And I think that's the flip side of the coin that is often not talked about so much.
Mm-hmm. Since you talked about also autonomous driving, what do you think about Carla? So Carla is a benchmark simulator that provides the standardized settings with the pedestrians always moving in the same way. You can randomize them, or actually always have them acting in the same way. They also have introduced different types of accidents, and there is a competition running always with the same initial conditions. and they implemented a common task framework. Basically, you can actually, so some of the data sets, actually some part of the simulator is released, and you can actually see the outcome of it, while instead other parts you have to submit results, and they will evaluate so some parts will actually be hidden from the ground truth, and they will evaluate it, and they will post the results later. So that basically they prevent you from overfitting the task. What do you think about this benchmark?
Is that for me?
Yeah,
no, I think it's a good idea, but I think it's conceptually no different than AI Gym or anything like that, right? Where you basically have a bunch of tasks, like, you know, you take half cheetah, it's got a local mode. It's a very similar sort of idea, right? And in that spirit, I think it's a good idea. For people who want to work on that particular set of problems, absolutely.
Animesh?
According to me, I think there are two reasons why benchmarks haven't been very popular. One, manipulation is not the same level of cognitive problem as let's say object detection or pose estimation. Right? Manipulation, I would argue, strictly is a superset. It's like harder. There's more to do. So that's two. Also, manipulation is not one thing, right? As David said, right? It's like is fridge door opening manipulation? Is opening a water bottle manipulation? Is cutting tomatoes manipulation? And if all of that, like all of the things we do with our hands, if we count all of them, then how do we create a set of tasks that is somewhat meaningful and evaluatable, right? Even though one could argue that many people are interested in manipulation per se, but if you start creating benchmarks like, okay, I have a benchmark of peg-in hole and gear insertion, suddenly that subset of people who are interested in that problem becomes very small very quickly. So that's one problem. And then two, there are, I would say, success cases where benchmarks did help. For example, I would say bin picking is one benchmark where exactly what happened, exactly that happens when you said that people take tables from previously published papers and they just sort of add a row to that, and you can do that. And we have seen, so I would say, I'm not worried about overfitting. I'm just like, people have not solved the problem of what would be a good benchmark in robot manipulation per se.
Yes, please.
But so hold on, people still do that also in RL and whatever. I mean, this is what the AI Gym results are about. This is what Atari Suite's about. This is, you know, it is.
But exactly. It's questionable. It's questionable. No, I'm not saying, for example,
I agree with it's questionable, but it does happen, right? It's not like it doesn't happen.
And that is why we as roboticists always question the progress in continuous control and error.
Do we? Okay. Sorry, I'll get on board with that. All right.
I have one question getting an aspect to the real experiment. So sim to real still looks sometimes like a trial and error or a talk, or we cannot predict if it will work. Are there any ways you can think of to do better in this respect?
Better in the sense that it's not trial and error, or better in the sense that we can make stronger statements about it working? Sorry, you may have to come back to the microphone then. I'm sorry.
that it's not trial and error. We can predict if it works, or give some bounds how, you know, in terms of how well it will work on the experiment. So, for example, if we make assumptions how different the experiment is compared to the simulation in the worst case, we could kind of make some kind of claims how in the worst case our learn policy and simulation is in the experiment. Does that make sense?
Yeah.
Is that even doable in the most general case? because to make any sort of statement, you would need to make some sort of assumptions of the scope of the problem, and the scope of, let's say, variation in a sense.
Could I pick that up? Because it's sort of a rhetorical question, I guess. I think that there is so when people talk about sim to real, they tend to talk about the simulation as some form of privileged thing that is, as if this wasn't a generalization task, right? I mean, whether it's a simulator or a different task in a different domain altogether is not really different, right? So in a way, what you're asking is, can we guarantee that something will generalize well, I guess? And I think the answer to that is no, we can't. At least I don't know how to. I do think though that there are ways of optimizing, of improving the efficiency of doing sim to real. I think that is undoubtedly true, and I'm not convinced that enough of us have actually looked at that problem. And I do have some ideas around that, but I don't think you have to randomly, try grid search of all things. I think we can do better than that.
Yes.
Indeed, we can maximize our chances, but I would argue it's a bit of a chicken and egg problem in the sense that it's highly dependent on what the solution is going to be and what really makes a difference and whether it works or not. And that's something you don't know when you're starting.
I think this question is very, very interesting, right? So I think that there is not enough thinking about the nature of the sim to real problem. It's not even formally defined, at least I'm not aware of that. Right? So what is real? Right? I mean, I was in my presentation, I was saying that, well, is this new? Is that sort of we encounter a new problem here? Not really, right? So the control theorists have encountered this problem a long time ago, right? In the worst case, they have to guarantee against all possible disturbances and the control very stable and so on and so forth. This is one kind of guarantee one can try to seek. Of course, if we take it to this level, then the kind of guarantee we can make is relatively weak, right? So I think that in order to come up with formal statements about, I think the nature of the problem, I think first of all, we have to define the problem formally. And then we have to recognize that the kind of statement we're going to make is necessarily, very likely we'll have to rely on our assumption about the reality, right? So now, in this sense, are we still calling that sim to real rather than, or maybe it's more just a transfer problem, right? Transfer from one domain, the source domain to the target domain. Yeah. If we agree on the formalization problem, and then suitable mathematical assumption can be made, and maybe that the theoretical results can be derived from that, right? But again, mathematics has this characteristic that garbage in, garbage out. Right, so like I said about the Lincoln Lab people, I can tell them about formal guarantee. They will come back to me saying that here is the 6,000 data sets. If it's do well on that, I'm happy. Right?
Anyone else would like to comment? Animesh?
No, I don't have anything meaningful to add here.
So yes, please. There is a question from the audience.
Hi, professors. Yeah, thanks so much for your talk today. I'm Chenja from Amazon. So the keyword we heard about a lot of times today is about differentiable. So we heard about like a differentiable physics simulation, differentiable algorithm network. So of course there are a lot of like advantages, but I want to know what do you think, like if there's like disadvantages or like potential problems of making it differentiable. And also a following question is that assuming we have a perfect differentiable physics simulator, under today's topic of simulation, sim to real, what do you think is still challenging? Thank you.
Right, let me take a step on this. Differentiability is great for computational reasons, right? So without differentiability is, if you think about the underlying world as some kind of function, then if I may assume that it is a function is differentiable, that enable me to perform computation much more. I mean, basically, I'm assuming certain kind of smoothness of the function that makes more computation much more efficient, right? Now, if I don't have differentiability, I still could have other alternative ways of optimization, and that just makes slower. And in fact, that if a human engineer has to update parameters and stuff like that, most likely we are doing some kind of greedy methods, but we cannot do different derivative in our brain, so that we are slower than the machines and things like that. Right. Now, in order to make those simulators differentiable, of course, a cost is paid for that, and that is the computational cost. So we have to balance the cost of the good things about the differentiable simulator versus the cost that's paid for it, and make sure that the end outcome, in fact, are getting more efficiency than the cost I paid for that. Right. Now, problem with differentiable simulators, I think that well, it's about derivative, right? Not all things, unfortunately, the world is not quite always differentiable, right? I mean, like if you think about contacts and all those things, that's unfortunately not differentiable. Of course, that over time people come up with marvelous tools in order to overcome these technical difficulties. But we just should keep in mind these are all nice approximations. That we cannot, I mean, derivative still becomes large, and the things becomes unstable, and these are the computational challenges that we encounter.
Ingmar, yes, please.
In reply to the second half of your question, even if you have a perfect simulator, then the question is, what are we actually simulating? Or what does your perfect simulator assume? Is it about physics? Yes, that brings us quite far, but then if you're really thinking about also interacting with people, we also suddenly need a perfect simulator of a human being, which I think is even further in the horizon.
So we have prepared also another interesting question, which is, so in the real world, there are many corner cases. So there are things that can happen very rarely, but they happen. For example, they can cause a fatality with an autonomous car. So how do you bring corner cases into the simulation? What are the best ways to deal with corner cases and how to bring them in simulation?
Can you give an example?
I would like to hear from you guys.
Now, what do you mean by corner cases?
Okay. For example, in autonomous driving, some corner cases are adverse weather conditions. So rain, hail, snow, and so on. Or the sun in the field of view of the camera that causes also fatality twice in autonomous driving, Uber, Tesla, and so on. So we know that Tesla, for example, is incorporating corner cases in their simulator. They gave a very interesting tech talk about that. And I want to hear your opinion.
But in a way that throw this question back to you. For example, you just said that corner cases, for example, fog and things, all those things like that. Since you already know these things are difficult, in what sense are they? And they are difficult and they're going to happen. In what sense are they corner?
They are corner. Okay. Yes, it depends. They are corner cases in the definition of the testing, in the description of the testing environment. So now, for example, if you think of autonomous driving at the moment, you know, what is very difficult is to predict things like people jumping suddenly on the street. I mean, think of, for example, the accident that happened with Uber a few years ago, where someone was on the highway and suddenly it appeared in the field of view of the LiDAR, and that was not expectable. These are basically corner cases.
In a way, I think what you're asking there is the sim-to-real question in disguise again, right? Because in a like the reason why I care about simulation in this context is I can set up any setting whatsoever, right? And so bringing the corner cases into the simulator, I think, isn't really the problem. I think the question is, can we do anything useful with the output of the simulator? Which brings us back to the sim-to-real question, right?
I think I would like to even argue that I'm with Davide in this. The corner case is like this problem of long tail, right? There is some environment setting, whether in observation or in state distribution, that you could not have procedurally generated upfront, or you did not. You could have, but you did not, for whatever reason. And you encounter this at inference or test time. Now that you've seen it, what can you do about it? Especially if it's very rare. So you're not going to see a lot of accidents, but you prefer that there are not very many now that you've encountered one. I think one way to argue is that, first of all, I think we are making a lot of assumptions. I don't think it's very straightforward to take a real world corner case back into simulation without a lot of engineering. That's one. So we should, I think about processes which can automate what you would call replay. And two, mechanisms of data augmentation around a corner case can enable algorithms to make sure that now this is in your library in a sense. So you can build a lot of augmented data around this particular kind of error mode so that at least in the future, this is not an error mode. There'll still be new error modes, just not this one.
Unless, of course, sorry.
Okay.
Yes. Okay. I want to go back to the benchmark question. Could we democratize benchmark selection by asking everyone to release the code, at least to initialize the system in the state that it was tested in the paper? Not necessarily the whole algorithm, just like this is how you think where I started this in my paper, and if you want to compare to a paper, you use that, and then you can copy and paste the results. Like, would that be useful? Is that something that people already do? How hard would it be? Does that make sense?
Yes. Anyone would like to answer?
So the question was, can we do the benchmarking by asking everyone to release their code? Is that the question?
No, can we, well, not the code for their algorithm, but the code to set up the simulation to the conditions that they tested their algorithm.
Right.
Does that make sense?
Yeah.
I think partially it depends a bit on into how much detail you need to go. Ideally, reviewers should complain about it if it's not in the paper anyhow. And if you look more at the machine learning community, like Joelle was saying, there's a big push towards making it a habit or almost a requirement to release code for your algorithm anyhow. So I believe that's a better way to make that a habit, that people are releasing their algorithm and not just do the kind of the small step you're proposing.
And in a way, it's similar to a data set release, right? So it's not just code that we're releasing. So for NeurIPS, we do that. For ICRA, we do that. We release the code, we release the data set.
So one last question we have prepared is, so we have seen that real-world competitions have helped to propel the progress in robotics. Would a sim-to-real competition help?
I'm so sorry, you broke up at exactly the wrong moment there. Would a simple what break help? I mean,
would a sim-to-real competition help? So organizing a sim-to-real transfer competition in robotic conferences help? Would it help basically address this sim-to-real gap problem?
I would argue that sim-to-real is more a means to an end. We want robots to do something useful in the real world. I personally don't care that much about how it's achieved. So I think it's better to propose competitions that are based around a task rather than sim-to-real as a method.
I'm undecided about this. I think that if we can identify a meaningful set of tasks, and well, I guess my answer kind of a little bit like what Jan is saying. Right? So if we believe that their sim to real is a promising approach for a set of tasks or representative, the set of representative tasks that kind of embody the challenge vision for sim to real, then that would help. But at this moment in time, that's not entirely obvious, right? So we could do things for specific tasks. Like, for example, I think the navigation and the driving tends to be of that kind. But yet that in that domain that they have already advanced enough, not necessarily clear that more sim to real would necessarily help research in that direction. And yet in places where we need help, and that we probably don't necessarily agree on, that's like I think is implying that we necessarily agree on we have to do sim to real. Right?
Ingmar and Animesh, do you want to make any last comment?
I think a sim to real competition would be useful if you pitch simulators against each other. So make it a competition about which simulator can bridge the gap with the least domain randomization. That I think could be a useful thing.
Yeah. I think broadly sim to real competition, it's not as if we don't do it, right? We already do it because look at like the DARPA challenges. The first phase of those competitions is actually indeed simulation. And if you look at the final leaderboard, it turns out that the sim to real part doesn't really work because those teams did get into the competition based on the fact that the simulator worked. I think two parts are needed. The first part is what Ingmar said, or maybe a combination of what Ingmar and David said, that we need a set of tasks that sufficient number of people care about for sufficient length of time, right? Because setting up this challenge will take multiple years. And if people only care about it for 1 year, probably not very useful. The other aspect would be essentially running a sim to real challenge would be amounting to running robotics as a service, because you are providing the real robot with policy evaluation or sort of controller evaluation as a service. That only works if we do that somewhat at scale. There have been past efforts in attempting that. Like I think Robotarium was an effort. Some people at Google tried this with Berkeley. It has been a challenge mostly because scaling something like this and keeping it operational for multiple years is non-trivial.
Okay, so we can conclude here the panel discussion. Do you want to make some conclusive remarks?
Thank you so much.
Yeah, thank you very much, everyone. That was, I mean, that's the end of ICRA, right? We did it, we made it. First, I want to apologize for the interruption in the middle. Some things we don't have control over in the Zoom setup, and this workshop is a little interesting. But also, thank you so much to the speakers. That last discussion was fantastic. You guys really did a great job. And to the co-organizers, Jacopo here, Sep doing social media, Siki helping out, Angela here, and Davide doing a great job as a host and great talk. And also offline, we have Melissa and Justin and Lucas helping out as well. We just have Angela's going to give you like 2 final remarks, and then we'll see you later.
You go first.
Yeah, go ahead.
Yes, I just wanted to add a couple of words. We've been speaking a lot about simulation benchmark competition, so some shameless self-promotion. We're organizing a competition simulation side and a real side that will be open for remote access at IRIS. David is also one of the co-organizers. Again, there's already some software available on our GitHub if you want to have a look at it. And there will be more software available through the summer to start participating on the competition, and more available. Go check out dynasysLab.org or saferobotlearning.org.
So this is a safe robot learning competition that happens for the most part in simulation, but we also want to transfer it on real crazy fly platforms. So if you are interested, yeah. You just remember saferobotlearning.org, and there you should find all the information.